Hello, everyone. Thank you for staying until the last keynote. Hopefully, it is interesting as all the sessions have been during this great day. So, the subject of this session is around Oxia, or about how scaling Pulsar to handle 100 times more metadata that it currently supports. And my name is Matteo Merli. I'm the Apache Pulsar co-creator, and I'm also the PMC chair, and I'm the CTO in StreamNative. So let's get to it, and let's first start by talking about what is metadata and how Pulsar uses metadata. So we're talking about metadata, and some people really are a bit confused and say, okay, what is that? And you can think about Pulsar as it is a distributed system, and the purpose of Pulsar is to store data for short or longer amount of time into a cluster of machines. And the first use case for metadata is that, okay, we can store data into multiple servers, but now we need to know where is my data, where can I locate, which machine has my data, which file, which location in that file. So this is kind of like a pointer to the data. And the other part is how to coordinate a cluster of nodes. Again, this requires information to be stored somewhere that is very reliable and accessible, and it also requires some propagating information from multiple nodes. To give some example of these pointers to data, like a real-world example from Pulsar use case. And so one example is that we have Pulsar uses Apache ZooKeeper, as most of you already know, and ZooKeeper has a concept of ledgers. A ledger is a log, and a ledger basically is associated with a number of bookies or storage nodes. So, and each ledger will have a different set of bookies, which is a good thing because now we can use all the cluster, we can expand the cluster, we can do all sorts of things. But to do that, we need to know this particular ledger, which set of bookies is associated with. And therefore, we need to store that information somewhere. And in this case, would be like the metadata for the ledger. That metadata will also contain more information, such as how many copies do you want to keep of the data, what is the write quorum, up quorum, what is the CRC algorithm to be used for this ledger, and some of the information, which topics this ledger belongs to, and so on. So these are all pieces of information that are attached to this data, that is a ledger that is stored into multiple storage nodes. Another example in the Pulsar side is the topic metadata. So when you create a topic in Pulsar, the existence of this topic is marked by some piece of metadata that is stored somewhere. And that piece of metadata basically contains, the core of it is a list of ledgers. So that keeps, okay, we have multiple segments that represent the storage of this topic, and this is the list of segments. And now we can either create a new one and append it to the list, and then delete it when the data is deleted. So this is another piece of information that we need to keep around, and this is of vital importance, of course. Another example, I'm just like doing a very short summary here, but is a schema registry. So Pulsar has a schema registry. The schema registry will store the schemas for the topic into ZooKeeper ledgers, but we need to keep the mapping between the schema X for topic X and where the data for the schema is stored. Hence, we need metadata. So this is just a few examples. There are several others that we do and to store pointers to data. I told that the other example is cluster coordination. Cluster coordination is kind of like a more advanced version of these pointers to data. And cluster coordination, it means, for Pulsar perspective, means to be able to answer some of these questions, right? Which bookies are available for me to use? Which among these bookies are read-only and which are read-write? If one book is down, I don't want to attempt to store data to that bookie or to read data from that bookie because I will know that I will try to write to a bookkeeper that is available so that I already know it. And so on. The other one is, for example, like the service discovery for Pulsar brokers. A client, when it comes up, will need to figure out which broker owns a particular topic, and there is a complicated mechanism by which the topics are assigned to brokers. But at the end of the day, that has been stored somewhere, and if one of these broker crashes or gets restarted, this ownership will change. So this is not just a pointer, but it also has to be very dynamic, so that if this broker crashes, the ownership is automatically released, and therefore we can assign the ownership to some other broker. Similar, like we need to, in many cases, we need to figure out what are the available servers, brokers, and that is kind of like a dynamic list of the brokers that are currently up and running and they can maintain a session with metadata system. Another one, which is very, very important as well, is I want to know what is the current load on each broker. Now I need all these brokers to communicate in some form, like their current usage and the CPU availability, usage, memory, and so on, and network utilization, for example, for the load balancer, so that we can have a clear and up-to-date picture of what is doing, every broker is doing. So this is just few examples, and but hopefully it does give some overview on what we intend for metadata and what does that mean in the context of Pulsar and Bookkeeper. Now, since we're saying that we are going to change metadata, I want to kind of give a bit of context here of why we're doing this, and what are the problems that we have in the current state in Pulsar with metadata. So Pulsar metadata has been pluggable now for a few releases already, since 2.10, and there are too many implementations, ZooKeeper and etcd. There are a few others for testing and for standalone, but these are the two ones that are for cluster usage at this point. Now, these two systems are very similar between each other, and most people will be using Pulsar with ZooKeeper anyway. But the point here is that there are several limitations in how these systems are designed that prevent Pulsar to scale to use more topics. And this has been a factor throughout the years, and we say that Pulsar supports a lot of topics compared to other systems, yes, but we can support million topics, few million topics in a single cluster, which is great compared to other systems that can only support a few thousand at the very best. At the same time, if we could use more topics, or if we could support more topics more easily, that will open up many more use cases. So that is kind of like the reasoning here. If you're looking at what this system provide, is that ZooKeeper and etcd are very similar. They kind of like use different consensus algorithms, but the architecture is very, very close. And the common thing is that they're not horizontally scalable. So you cannot just add more nodes into a ZooKeeper or etcd cluster and have more throughput or more storage capacity, because every node will have the same entire data set. And you can vertically scaling by adding more hardware, more CPU, memory, but it only gets you like minimally improvement. You're still bound by the capacity of a single node. And more so is that these systems, both of them, are quite inefficient at storing a large amount of data. And the main reason is that they're using a concept of snapshot. So ZooKeeper and both ZooKeeper and etcd, they will have a transaction log and a snapshot. Every X amount of transaction, they will have to dump the entire data set into a new snapshot. So every X transactions, you're going to be writing the entire data set again on disk. Now that involves a lot of I/O, and after one or few gigabytes, basically it becomes very, very inefficient. And when you're taking this snapshot, it is stealing all the I/O in the machine, and it causes all sorts of trouble. So that is one reason why you can't have a lot of the data into a single ZooKeeper or etcd cluster. So to solve all these issues, we have been thinking a lot about this problem space, because it has been a recurring theme, and we came up and we kind of like have our solution with Oxia. So this is why we've been introducing Oxia. So what is Oxia? Oxia is a system created and open sourced by StreamNative to solve this metadata and coordination problem at a large scale and without making any compromises or any sacrifices here. The main theme for Oxia is that it uses a new architecture that is assuming a more modern environment, more cloud-native environment to deploy with, and so we can take advantage of this environment. We don't assume that we are deploying into a bare metal, although it is technically possible, but the main focus here is to optimize for containerized Kubernetes environment. And because these will give us many advantages, and we don't have to re-implement a whole number of components that can be quite tricky to implement. So if you're looking at our goals for Oxia are, this is a kind of the thing that we really typically care for inside such a system. So we want to have linearizable per key operations, and we don't care about the global linearizability. So we don't care about having atomic updates over multiple keys. That's not something that we typically use, and is a feature that will require sacrificing a lot more flexibility than what we want. And because we only have per key operations atomically, therefore it becomes much easier to have transparent horizontal scalability. So we want to have a system that is able that we can just add more nodes and have more capacity, or we can remove nodes and reduce the cost of the system if the load goes down. That flexibility is really, really important. It is designed to handle millions of read and write operations per second, even in a small cluster, but it can scale up horizontally. So there are no bottlenecks in the data path after scaling up. It is designed to store a large amount of data. Now, we're talking here about 100 gigabytes. Again, we're not writing a database here, so we are not designing for hundreds of terabytes or petabytes, nothing like that. We are targeting, in database term, is a small amount of data, but for where we come from, like ZooKeeper etcd, hundreds of gigabytes is a huge amount of data. So that's kind of like the ballpark of where we want to be. And again, we're seeing that this is not a database, and so we don't care about some of the features that the database have and provide, but we do care for something that databases typically don't provide out of the box. And one such thing is the ephemeral records. Ephemeral records means that you have a session open to the metadata system, and such that I can create a record, and if I crash and I'm not able to reconnect within a certain time, this record will automatically disappear. And so these are important and needed for all this cluster coordination, because you can have kind of distributed locks, you can have leader election, you can have service discovery implemented on top of these ephemeral records. Another Oxia feature and goal is the namespaces. So we want to basically have control in different ways of controlling different parts of the metadata. So we have added namespace support, and so we can have a different level of isolation, different configurations, and treat different namespaces in different way. Another feature that is out of the box and like first level citizen here is notifications. And notification basically is kind of like a CDC. I can subscribe to a namespace and receive all the updates that all the changes that happen in this namespace. These are important if you want to keep a cache of the data, because you can basically have this revalidation option on the and automatically revalidate the cache. Now I'm going to be diving a bit more on how we started this journey of designing Oxia and what the decision that we made are. So we say that what to design for scaling, and in Oxia each namespace is independent, and each namespace is also divided in shards. You can think of a namespace as the database table. Now shards are also independent and are assigned to all the available servers. You have multiple replica or single shards, and they're all like spread across the cluster. So when a cluster expands or shrinks, these shards can be reassigned. So we can go from, say, 5 nodes to 10 nodes, and automatically the shards will be reassigned automatically to the 5 new nodes in a graceful and coordinated way. Shards can also potentially be split when they're big or they have too much traffic on it. Now, this is not yet implemented, but this is the next thing that we have been working on. So with the shard splitting, then basically all these concepts of shards and how many shards do I need become basically irrelevant, because now you can just start with one single shard, and then the system will take care of splitting as needed. The other big mantra that we have adopted in designing Oxia has been to do not reinvent the wheel. So typically, like, these kind of systems are implemented using consensus algorithms for the data replication. And the reason is that you want to have a strong consistency. Now, we do want to have strong consistency, but as I mentioned, we are using Kubernetes as a target environment. Therefore, we have some primitives that are available for us already. And one such primitive is a config map. So Kubernetes has config maps. Config maps, I can use them to store and read data. And I can do also compare and set to have atomic updates. Now, we can use this config map to checkpoint the cluster status. Because of that, basically, we are deferring the consensus implementation into Kubernetes. And instead, we focus on the log replication. So we have implemented a log replication model that is no-failure tolerant, that is very fast and very easy to optimize and implement. And when there's a failure, then we basically roll back and perform some recovery mechanism that, using the cluster checkpoint, it is able to connect to the storage servers and figure out what is the last entry committed, and then we can move on. So basically, the data plane is decoupled here into control and data, and then we have a fast and simple data plane, and then the control plane helps in the safety and the recovery after errors. So if you take a glance at the architecture, we have several components, and I will dig a bit into the what do they need, what are they needed for. So we can start by the client. So if you look at the client basically Oxia gives you an SDK, which you have these familiar key value APIs, put and get and delete and so on. And the communication is based on gRPC, so it's very easy to add new client libraries. And currently we support Go and Java. And so the client library will take care of the server discovery and data path talking with the storage servers. Next one is the storage pods. So we say we can add any number of storage pods. Each storage pod will store data locally and will participate in the data replication. So the storage pods is where all the clients will connect to, and each storage pod will be assigned a number of shards, and it will be either the leader or the forward for these shards, depending on what the coordinator says. So a shard is actually only served for read and write requests from the client by the leader, and therefore we can have this store consistency model. Next one is a coordinator. So coordinator is kind of like unique to Oxia in this case, but essentially the coordinator is a single process that it does perform the control plane and the health monitoring of the storage pods. And when it detects that a storage pod has failed, if this storage pod was the leader for some of the shards, the coordinator will initiate the leader election. Same, it will also initiate like a cluster rebalancing if you change the shape of the cluster. So if you go from 5 pods to 10 pods, the coordinator will say, okay, this is my new desired state that I'm reading from this cluster config map. And I will apply all the necessary changes to get into the desired state. And the coordinator also uses the cluster status as the checkpoint. Whenever a new leader is elected, whenever a new term or epoch is created, it will be checkpointed into this config map. So these are all like very infrequent updates, only when there is failure and so on. The last one here is the operator. So this is a cumulative operator, and the role of the operator here is to take a CRD with the description of the cluster and convert that into the cluster config and start all the pods and all the Kubernetes resources, of course. So for example, the administrator here could create a CRD saying that I want to have an Oxia cluster with 5 storage pods. I want to have these two namespaces with 3 shards initially for each of them and replication factor of 3. And by updating that CRD, we'll create the cluster and it will make the coordinator to perform all these changes. Now, after sometimes you can either create a new namespace or expand the cluster, or like perform also all these sort of operation, and the operator will update the cluster config, and the coordinator will comply with that. If you're looking a bit more in depth at how data is replicated, so we're saying that there is a leader for shards, it's elected by the coordinator, and there are followers. Depending on how many replicas you want to have, there will be more or less followers. So all the read and writes are going through the leader, and the leader will push all the updates to the followers. Whenever the leader receives enough acknowledgements, it will also apply into the local key value store. So first it gets applied into the write ahead log, and then it gets applied to the key value store once it is fully committed. Now the followers also will apply for all the fully committed entries to the key value store. And the reason is that a follower basically it is very close, it is tailing the leader very closely, so that if the leader crashes, we can let a new follower very quickly. So that you just have to apply the last few entries, and then it can be promoted to leader. Moving forward, so I think this just gives an overview of some of the decision, just a small subset of the decision we took when designing Oxia. And one of the most important aspects for implementing Oxia has always been to validate Oxia. That means that Oxia is really a critical system, right? So this metadata, sits at the very core of any distributed system. So if this system is not reliable, stable, or resilient, or any other kind of errors, it affects in a very bad way Pulsar cluster, for example. Like, so if we lose a bit of metadata, we can lose a lot of data in the end, right? So if you lose all the pointers to the data, you're going to lose a bunch of data, because you have the data there in the storage nodes, but you have no way of accessing that. So it is the same as losing the data. In the same way that if the responses from Oxia are getting slower under certain conditions, or are giving some unexpected errors, they're also going to be making a problem for Pulsar using Oxia. Therefore, we started using different ways of testing Oxia, and with different approaches. And this approach has basically guided the whole design and implementation of the system. So the first one has been TLA Plus. So TLA Plus is a high-level language that you can use to model distributed and concurrent system. That means that you can write within its own language and a specification of what the Oxia data replication protocol is. And then once you have written this model, the tools from TLA Plus, they can take this model and run it. And that means that the simulator will run through all the different states that this protocol and mechanism that are reachable. So you define your boundaries, and then it will explore all possible combination of different components in the system, the state. And so this is more like a mathematical exploration of all the possible states of the system. Now, at each step, it will validate that the basic assumption are not violated. In this case, what makes sure that is that the log replication always ends up with all the replicas having the same sequence of entries in the log. So that is the main thing. So we can run the Oxia model through TLA Plus model and tools, and we validate that. So that validates kind of the model of the replication. Another way to testing that we have been adopting is Maelstrom. So Maelstrom is a tool that kind of like make it easy to run Jefferson simulation. So Jefferson typically requires to deploy a cluster and then injecting all sorts of failures and then validating the consistency model of the system. So Maelstrom is a tool that instead of like running in a cluster, you can run everything into a single node. If you run everything into a single node, now it makes much more easier to inject failures. So for example, like Maelstrom can generate a workload. In this case, it would be like a linearizable key value store kind of like workloads, having like write, reads, compare, and set, and this kind of requests. And then it will trigger failures, either delays or like messages get reordered or any kind of errors in the communication between clients and servers or between servers and servers. And one of the most interesting part for Maelstrom is that it is really testing the real production code. So it's not testing a model of the system, it's testing the real system. And the way it works is that instead of like using a cluster in multiple machines, it is spinning up multiple processes, making a multi-node cluster into a single machine. So you can run that in your laptop and say, I have a cluster of 10 Oxia nodes. And both Maelstrom to talk with Oxia servers and between them, the Oxia process will be using SD in, SD out. So not TCP networking, but instead like writing JSON commands on the SD out. So basically, we swap out gRPC for this SD in, SD out transport, and but everything is the same. So all the controllers for their leader election, so everything is real production code. So this is like a very valuable tool that can discover like a whole class of problems in the system. Last one here is a chaos mesh. So chaos mesh again is another different approach to this problem, which is we deploying in Kubernetes, we can have a load generator running, and then we can use chaos mesh to generate a whole sort of different errors and simulated failures in the Kubernetes cluster, from networking issues to pods getting restarted, processes getting killed, and all sort of network partitions and so on. So it's very easy to generate all sort of different failure scenarios and see and validate how the system behaves under these conditions, and that the result is not only correct but is as expected. So if I kill a node, I would expect the system to recover within a certain amount of time, and we can validate this using chaos mesh. So I hope this was a gentle introduction to Oxia and explain a bunch of the reasoning around Oxia and why we implemented and what were our goals in doing so. But essentially, one takeaway here is that we designed Oxia really to resolve the metadata scalability problems in Pulsar. We want to take Pulsar to the next level in terms of how much metadata, how many topics we can support, and so on, and how easy this should be. But we also believe that this is kind of like problems that are common to many other distributed systems that store data that needs metadata and needs coordination. And so Oxia can be useful in not just for Pulsar, but for many other systems. And why should you care? Because basically the plan for Oxia is to remove all these hard limitations for Pulsar and make it very easy to run many millions topics in a Pulsar cluster. And also, like one of the benefits here is that we want to remove also namespace limitation in Pulsar to have number of topics. Right now, the recommendation typically is around 10,000 topics per namespace. After that, you have to break it down into multiple namespaces. That's purely based on limitation in ZooKeeper, in the way that it can fetch the list of topics in namespace. So we don't have to have that limitation again when switching to Oxia. So I talked a lot about what Oxia can do today for Pulsar, but when you start thinking about it, there are several other use cases that are really interesting that we can explore. So once we put Oxia in, now we can have a reliable and scalable key value store. So many of the problems that originally we were either using ZooKeeper or we were not using ZooKeeper because it was not scalable enough for these use cases. Now we can rethink a bit of them. One example is cursor positions. So right now we store them in ZooKeeper using ledgers. Now it works, it's scalable. It's also very complicated, but we did that because we didn't have a better way of dealing with that. So if we were to switch this use case into Oxia, we can basically have a much easier way of dealing with the cursors and manage cursor in Pulsar because we just basically key value access. So we don't have to worry about managing the ledgers manually and compacting them and so on. So it will be a much easier implementation. Another one is Pulsar function state. So Pulsar functions can have a state. Right now there is a ZooKeeper table service, but we want to eventually migrate that to support Oxia as well. Or things like system topic policies that are using topics to store the topic policies. Again, the reason for doing that was because it was not scalable to do so in ZooKeeper and so on. And thinking a bit more down the road, we can also see how we could use Oxia to enable a much large scale compaction mechanism. Right now, compaction is assuming that you can keep the keys, the set of the keys in memory at all time for doing the compaction. So it is doing that in two passes. But what if you have millions and millions of keys? Then in a topic to compact, then it could become a problem. Instead, if we could offload this into a more real key value store, we could remove this limitation. So having said that, I would just encourage you to try Oxia. So go to github.com/StreamNative/Oxia and give it a try and give suggestions and try it out and tell us what you think. Thank you and have a nice day. And thank you for participating in Pulsar Summit. Bye.